All right. So, so let me just introduce these terms if somebody is unfamiliar. Representation learning basically means that we are discovering these features automatically. Like earlier, we used to manually decide all the features for any given data, and we want to do tasks. But now with the advent of deep learning, all these features are discovered automatically. So we just plug in the data, run an optimization algorithm like stochastic gradient descent, and these features are automatically learned using loss functions, optimizing appropriate loss functions. Now, for supervised learning, which is the most popular form of this deep learning, is basically you are given some input data, you predict some output labels, you put it's just like linear regression basically, but just the model is not a as simple. It's just a neural network of some sort. Supervised learning, I'm hoping everybody is familiar with. In case you are not familiar, please let me know right now. All right. So now coming to self-supervised learning, as the name suggests, and it used to be earlier categorized as unsupervised, but now the name self-supervised is considered more appropriate, because it's basically, if you think about an autoencoder, it's really based on just trying to recreate its own input, which is like data itself provides supervision. So you don't have explicit target labels, but you create these supervisory labels automatically from data. That's really important, because manual annotations are costly, and that's what's really needed for supervised learning. So as I've already said, kind of hinted to, that we'll focus on deep learning models during this presentation. And yeah, that's about it. Yeah, let me just move on to the next slide. Okay, so first of all, second question is why do we really want to do self-supervised learning? One answer is the most important point is actually the first one is, we have a ton of unlabeled data. You can scrape the internet. All these data streaming devices, mobile devices, they are collecting data. Your Fitbits, Apple Watches, they're collecting a lot of data, unlabeled data all the time. You can really utilize a lot of data, and we know that deep learning models are data hungry. So it would be a perfect match if we can use unlabeled data to train deep learning models. So that's what self-supervised learning can help us use these unlabeled data for learning representations, because labeled data is costly. There are other secondary advantages. People have shown that in certain cases, these self-supervised representations are more generic or task agnostic. They can be basically used for multiple downstream tasks, better than a supervised learning. So basically, for supervised learning, you are doing one task. Say you are telling image is a dog or a cat, and you cannot maybe use these features to say something else, like whether it's day or night in the image, or something totally different. So using those learned representations, but self-supervised representations have been found to be more generic, easily transferable between more easily transferable between tasks. Another advantage is they help reduce dimensionality of features in when you don't have labels, and that's a very significant computational benefit for certain applications like natural language processing. So word2vec is one of the most, like, how to say, revolutionary work of NLP that really changed things around. So basically, for words, you use one hot vectors which are the size of the vocabulary, which is like million dimensional vectors, and creating neural networks for such million dimensional vectors was a challenge. So basically, using self-supervised learning, word2vec tries to compress these million dimensional vectors into a continuous vector. And details of the work, I think I forgot this reference, so I'll add it later, but you can read more about it. I'm not going to cover in detail that. Finally, contrastive methods can also help disentangle or create modularized representations. I'll show an example of it in a few minutes. So what is the typical workflow in self-supervised learning? What we do is we create these, invent these pretext tasks, as we'll call it. So this is not our main task. This is not what we really want to do, but we still perform that using this network, deep network. And the idea is that it will give us these representations Z. Can you guys see my mouse pointer, by the way?
No.
No.
Yeah, no.
All right, how about now?
Oh, yes.
Okay, great. So so as I was saying, so we invent this pretext task, and what we want is really this Z. We want this representation Z to be learned from this input data X, and we train this encoder to solve this pretext task. Then we take this encoder. We don't care about solving pretext task. We care about something else, a downstream task. And we take this learned representation and try to solve the downstream task using this representation. So that's the typical workflow of any self-supervised learning problem. A downstream task is, can be something like a simple classification problem. And let me show you some example to make it more concrete. So this is one of the most, I would say, initially, in computer vision, this was the most popularly used pretext task. It's called instance discrimination, and the idea is very simple, demonstrated in this figure, that the same image on the left, you see a monkey's image, and below it is the augmented image. So basically that's the same image, and it has been applied some color transformations and some basic transformation, cropping and rotation. And so they belong to the same person, same object, exactly same image. So they're so let me not make it very complicated right now, but the idea is just we want those things to be similar because they come from the same image. And on the right side, you see those are negative, as it's called, negative image, and the original image. So it's negative to the original image because they don't share that feature. They don't come from the same image. They're totally different. And we want to, make them dissimilar. And what this making similar and dissimilar means, we'll cover in more detail later. And so this is the pretext task. This is what the network is trained for. But once it is trained, we take this learned representation and solve a classification problem from it. Say whether there is a monkey in this picture, or there is a tiger in this picture, or a dog or a cat, things like that. Now this is a more concrete example, and I just put in some result table as well. This is doing something. This is another pretext task of predicting rotation of an image. So given this image of Bulbasaur, if you know this Pokemon, we basically can create labels by rotating this image, and because we created that label, we know how much we rotated. So what we can do is give this rotated image and try to predict what is the angle of rotation. We don't require any labels, human annotations for such a task. And all the RoTNet paper does is give these rotated images of different objects and predict what angle they have been rotated by. And once the network is trained again, after using this pretext task, they train it, they use those features to get a classifier over those features for ImageNet task. And this table shows one of their results. And I just want to highlight the first row here, which is using regular supervised learning performance. which is 59.7% accurate. This is, by the way, 1000 classification. So 59.7 is pretty good performance. And the con 4 and con 5 just refers to what layer features were used. So there were 5 con blocks, and they tried to build a classifier on, you know, 4th convolutional block and 5th convolution block, and compared the performance. So for the supervised task, both were same. These are other, you know, other pretext tasks that have done, you know, their respective performances. And now finally their RotNet papers performance was, I mean, they reported they were best among the unsupervised works. So they showed 50% of the time they got accurate using Con4 blocks features. So you can see, like, it is very useful, it's very powerful. No labels were used for the RotNet to get that presentation. This is another, which I consider an amazing example of what can be done with self-supervised learning.
Can I ask a question?
Yes.
About the table you had?
All right. Yes.
So for one thing, I didn't quite get was all the pretext task methods was also you trained with 5-layer convolution so that you could take the Con4 and Con5 features from them?
Right. So to have a apples to apples comparison, they used the same architecture for these experiments.
And then after you take out the Con4 or Con5 outputs as the Z, yes, what did they train for the downstream task?
They had the classification. So they had a simple MLP, basic multi-layer perceptron, as a classifier.
So that's additional layers?
Yes. So use those features to have so they just train the classifier. They don't, similar to what we did in the radar paper.
And the ImageNet labels, yes, they were trained with that downstream task in place?
Correct. Yes.
Okay. All right. Thank you.
Okay. Okay. So as I was saying, so this is another, I would say, really good work, and it uses contrastive learning for an important step. And what this figure basically shows is you can create artificial videos of people saying whatever you want them to say. So this model actually takes 3 things as input. On the left, you see the identity reference. So say I will put your face in there, and then audio source. So you can use my audio from this, say, presentation. So this is the audio of this presentation. And then there is this pose source, which could be anything, how you want to move in the video, how you want your head to move in the video. And giving all these 3 inputs, you can create a totally synthetic video, which will speak what this audio is speaking, and move the head like this pose source is moving, and will look like, if you use your image, it will look like you in the identity source. Sorry, just a second. Yeah, so you can really, this is almost amazing and dangerous at the same time. Now coming to I'm going to briefly just talk about their model. So they use contrastive learning in so they use contrastive learning in this part, where basically what they use it for is 2 modalities: the video frame, which is an image basically, and the audio spectrogram. And they know that this video frame corresponds to particular, so like time synced audio and video, they should be close, they should be positive, just like the monkey example. They should correspond to each other. And the video and audio that is not do not correspond to each other should be far away from each other. Using this simple idea, they are able to learn this speech space embedding, which basically helps what part of the audio affects what part of the video. That's what it really captures. And I thought that in a completely unsupervised manner, and I thought their results were pretty amazing. And if just thinking about even a supervised learning, this is something really not so easy to do. This is more relevant to stuff we do maybe. So basically this is very recent. This is also 2021. I think it was a competition in Europe. So what these guys did, the competition was about trying to predict heart rate or PPG or PP, something close to a clean PPG signal using just a person's video. So the idea is, our skin is very slowly changing its colors as our blood pumps. So can we detect that in images and create a heart rate estimate of heart rate signal? So these guys, although the original competition did not specify whether you want to do supervised, they gave you the labels, they gave you the PPG signal corresponding to the video. These guys did it in completely unsupervised fashion. They didn't even use those labels, and they performed at par with any other candidate in the competition, just using unsupervised. I'm not going to go into the detail of the method. Their paper is cited, so you should go and check it out. But this is just really good, I feel.
I know you didn't want to go into detail, but maybe you can at least say what was the pretext task in this setting.
Right. So now so these pretext tasks are a little more complex. I did not put that their schematic of the model, but maybe I'll cover it in the session 2. Okay. I can cover if there is more interest about it. Okay. So yeah, so I'll remember this. Now, pretext task formulations. So there are two big categorization. By the way, if you read survey papers that I gave or any other surveys, it's not very, the taxonomy of contrastive or self-supervised learning is not established yet. So people are proposing several forms to categorize them, several ways to categorize them. And I'm using one of them, which I felt like would really aligned with me and would be much easier to explain. So there can be other ways of going about or categorizing all the stuff that is going on in the literature. So according to this categorization, the pretext task can be thought of categorizing into two main categories. Self-prediction, basically, which says that you take every sample and you try to create a supervisory label using that sample. So if you saw the instance discrimination task, we were using the same monkey's image and create a a positive example using the same image. Or I'll show you more concrete example in the next slide, but that's the main idea, that you use the same sample and create the label using that. In contrastive types of pretext task, you compare the relationship between two different samples from the same data set. So for example, the speech space of this PCAVS model was using the relationship between the audio and the video samples. So roughly it's intra-sample versus inter-sample relationships. So I'll talk about self-prediction tasks and how they look like, what are different types of self-prediction tasks. I think a lot of people would be familiar with the denoising autoencoder, which is basically, you take this image and you add this sort of random Gaussian noise to it, which is basically masking some pixels, and you try to predict the uncorrupted image. So that's again a self-prediction using the same image you created the input and use the same image as the output. So that comes under mask prediction. So we are masking certain random pixels. Other masked predictions are basically given a time domain signal. You can you can skip certain samples and then try to predict the complete signal. And more in an image-based side, you will have you can remove random part from an image and try to predict the complete image. So all these types of pretext task form can be categorized into mask predictions. And there's a lot of work, even like the very popular NLP, natural language processing word BERT, is based on this task. Generative models also can fall under this category. So autoencoder, as I said, it tries to predict the identity function, and either the usefulness of the features comes from the bottle, imposing constraints on the latent space directly. VAEs has this bottleneck. The variational autoencoders also have this bottleneck, a constraint on the latent space, as well as trying to make the latent space in the independent Gaussian. Now autoregressive models are doing self-prediction again, which is basically predicting step by step. So that is from using the time step t everything before t minus when you try to predict the future time step t. So this figure shows you the autoregressive, tell me this next sample given all the past samples. Similar autoregressive idea can be used in images as well by using something like a raster scan order. So you start predicting from here and predict next pixel using previous pixel. Yeah, so third category would be innate relationship prediction. As this is not a very scientific name, but it's under development, let me just say that. So basically you can form these tasks by there are other sorts of innate relationship among the data samples. So for example, the rotation task that we saw, predicting the rotation. So we understand that every pixel, when you rotate the image, every pixel has to correspond accordingly to form still a meaningful image, although it's rotated. There is another task like a jigsaw puzzle task. So basically you divide the image into these 1, 2, 3, 4 blocks, and then you jumble them up, and then you can try to predict the what was the correct order of these blocks. So you can try to solve this jigsaw of patches and try to reconstruct the image. That's another form of self-supervised pretext task.
So I want to ask something here. Yes. So let's look at that rotation example.
Okay.
The pretext task takes 2 images and figures out how the second one is, how many degrees is rotated from the first one?
No.
What precisely input and output?
Right. So there's a good question. Maybe that was a confusion I created. So self-prediction is really about one input, one output. It's not about, so that is contrastive. What it takes 2 images, one. So this basically, if you think about this task, it takes a rotated image and tries to predict the angle by which it was rotated. So the output would be the angle.
Without, I mean, how does it know that something is rotated? That's, like...
Because it will see the 0 degree samples as well, right?
Then it becomes, the task has to have both images as an input, as I was
yes. But I thought the confusion was like, it takes both images simultaneously. Yeah,
it does take both. It has to, otherwise how are you going to formulate the problem? The task has to take both images so that it can estimate how one is rotating with respect to each other.
Oh, yeah, I see.
How could you give one image and ask how much it is rotated by? Because the cat might be lying naturally. Correct. Is rotated.
Yes. Yeah, I did not think of that.
So then the latent variable representation you learn.
Yes.
is it a parallel network where you have two images going through a network separately in parallel, and then you get Z1, Z2, and then from Z1, Z2, you try to estimate the rotation angle?
I'm pretty sure this was a single. Let me try to see a detailed figure. I have it somewhere. Let me just try to pull it up. So I think this was the figure, and I still think this was okay. So I see. So what they did was basically created a classifier. So the way they posed this task was they put in 4 or 5 rotations, which they knew, and they created they created classes. So rotation 1 is class 0, rotation 2 is say class 1, which is like rotation of 30 degree, and so on. So there are like discrete set of rotations, and all of the images are in the data set, so including the 0th image, and they just train a classifier. So they have, for every image, they have class 0, class 1, class 2, class 3, class 4.
So when it comes to use it, you give one image.
Right, and it tells its class.
I just don't know how it could do that. I mean, why wouldn't a cat not be lying 90 degrees? How do I know that that's the 0 degree image? I mean,
so Professor, I see your point. So the thing is that,
how do I know?
Yes. So the thing is, there's something.
What's the name? Oriented.
Yeah. So I think something really weird about how this instance discrimination is formulated is every image is its own class. So if you think about, if we talk, we very briefly talked about instance discrimination, every image has to correspond to a patch of itself and no other image, even if the other image is of a monkey, so in the same spirit, although there can be an image of a lying cat, as you say, that image is, only the rotations of that image will be considered, so it will have all 0, 1, 2, 3, 4, 5. So every image is has to have all the 4 or 5 classes that we decided to. So in that sense, it's not very it doesn't make a lot of sense. But the idea is that every image has to his own class. So if there is a lying cat, it will have a 0 degrees. It will
we are talking about the Pokemon.
Okay, network, right? Yes, Pokemon. Yes. Let me try to go on the slide. It's really switching slowly on this iPad. Yeah. So every image has its own, class. So if there is a lying cat and there is an image of a standing cat, these 2 images are totally separate, forming separate 5 or 4 or 5 images of them.
So ImageNet has 1,000 classes, and they are exploding it by 4-fold or 5-fold.
Yes.
Okay. Well, we'll have to rank and Kim. Okay. Thank you. We'll come back to it if needed.
Okay, it's just a second. It's really slow. Okay. So so we talked about innate relationship prediction. The next one and final one would be something more hybrid. So something hybrid would be like first using, this is an example of a possible hybrid approach, first using a VAE or a VQAE, in this case, a special type of variation autoencoder, to find a latent space, which is this ZQ, this ZQ, and then further modeling this latent space in an autoregressive fashion. So the latent space itself is further modeled in an autoregressive fashion. So you can do nested self-prediction as well. So that forms the more hybrid self-prediction types of tasks. So now coming to contrastive learning, hopefully self-prediction type of pretext task made sense. And contrastive learning would be the focus from here on. That was just for me, briefly trying to describe self-prediction part. Now, the main idea, as I said, of contrastive learning is, bring similar samples close to each other and dissimilar ones, you push them apart. Now, saying something similar or dissimilar requires a notion of similarity. And that's something that we define. We decide what two data samples are similar to each other and what are not. And the reason we can say that is we have an idea of, some high level meaning to it, some semantics. So for example, if two time series, are aligned to, time aligned, we say that they correspond to each other. They have, they have some common information per se. So they are similar to each other. But if they are not time aligned, they don't share that information. And that's why they are dissimilar. Other examples would be if they are of the same object, say both images are of a dog, then you say they are similar. If they are one dog and one cat, then they are dissimilar. In instance discrimination, which we talked about earlier, every image is its own class. So basically, if the patch did not come from the exact same image, does not matter whether it's a dog or a cat, it should be the exact same image. It is dissimilar. If it came from the exact same image, it is similar to it. So there can be several ways to formulate this, and we'll talk about some from here on. Now, this is I hope you guys can read this. Is kind of pixelated due to my iPad screen sharing. But this was an image taken from review paper and really gives a brief idea of what's going on. The main motivation of the contrastive learning was like metric learning, and metric learning literally means this, that you have this data space where the A space here, which has similar samples. You assigned this notion of similarity, by the way. The blue ones are similar in your in some high level meaning, and you understand these similar samples are all jumbled together, and you want to find a space which kind of nicely separates them out and clusters them together. So normally we have this notion of Euclidean metric, which is could be like IL2 distance. And the purpose of metric learning is to find a metric space. Originally it was just linear, and find a linear transformation, the original formulation of this problem. And under that linear transformation, the similar points should cluster together, and dissimilar points should be pushed apart. And modern day is mostly about deep metric learning, where you're trying to, instead of a linear transformation, you're trying to do a new non-linear neural network transformation. Well, this is shared weights, so both have the same, these are exact same transformation, and you're trying to make them similar or close to each other if they are similar in your opinion, in your high level meaning, and if not, push them apart. So ideally the transform data space should look like this. This is a small example of doing this on MNIST, just 2 digits of MNIST data set. So these are images of digit 3 and 8, and you take them and you try to do the same thing with them. So hopefully images 3 should cluster together and 8 should cluster together. And as the network is trained, by the way, this is called CME's network, this sort of shared network. Sorry, Devin, can you just unmute yourself and ask?
Yeah, sure. I was just asking on the previous slide, just really simply. So the goal is that we want to learn the optimal nonlinear transformation, right?
Correct.
Such that clustering is okay.
Yes.
Thanks.
But I mean, also, you know, is there a notion of dimensionality reduction? Is the transformation mapping to a lower dimensional space where I can get the distance metric?
Yes. There
And
is a notion of dimension. Yes.
Once I go through the neural network transformation, is that distance metric Euclidean itself, or does it also have other ways of penalizing?
In the output space here?
Yes.
We're just going to talk about them in the bit, but the original short answer is originally yes, they were Euclidean based, but slowly people propose more models and different interpretations of more different types of losses based on different types of notion of distances, and we'll talk about them in a bit.
Okay.
So yeah, so just to briefly cover this, as the network is trained, the blue curve shows distance between average distance between dissimilar images starts to increase, and average distance between similar images starts to decrease, which is expected. That's literally what we are minimizing, so it's not very insightful. All right, so let me just talk about these were the original proposals in a paper by Chopra et al. In 2005. And what they were trying to do is face identification and face recognition using this. But just to present the idea more simply, we're just using MNIST digits in this example. And the idea is again the same: push the images of threes. Sorry, just a second. Yeah, so push the images of 3 together. So basically here they're just minimizing the Euclidean L2 norm. So minimize the L2 norm, and GW is the transformation, the neural network transformation. And if they are 8 and a 4, then push them. So they maximize that distance or minimize the negative of that. There is a more popular and more effective version of it, which does this in a groups of 3. So you have an anchor, which is the middle one here. So anchor is like, just let me just say it's an anchor you picked. So here it is digit 3. And then you have a positive sample corresponding to the anchor, which will be, belonging to the same class. In this case, that's 3 again. And a negative sample, which is 4 here. And you calculate a loss function based on all these 3 inputs. So the loss is basically, D1, which we want to minimize, minus D2, which we wanted to maximize. So we can minimize this. And there is an alpha. So people, introduce this alpha because, and I'll show you in the next slide, will make more sense. But basically it's for creating a margin between the negative and the positive sample. All right, so let me just talk about that really quickly. So these are the exact loss function. Contrastive loss is the most, here the figure in the figure A is the Euclidean norm base that we just talked about in the CME's network. And the exact loss function is mentioned here, where this Euclidean distance we are trying to minimize between the positive pairs, and we are trying to maximize distance between the negative pairs. And there is this component of margin or alpha, which is what is trying to do is suppose we did not have this alpha. So what can happen? So what can happen is the network can really collapse things into single points, so their distance would be 0 from each other. And it's really important to include that margin in there. So if you see this figure, this is the anchor point in the triplet loss, and this is the positive example. So we are trying to minimize their distance, and the negative sample should be at least alpha far from here. So That's why this alpha is the, the idea of introducing a margin there. I'm not, so quadruple loss basically introduces two margins, and it creates loss based on 4 pairs. It's just based on triplet loss. You introduce an extra sample, which is also a positive sample, and you introduce two margins. It's not very used. It was just one paper somewhere, and it's not very popular, so we're not going to talk about that more. But structured loss is what we, what a notion, a form of structured loss is now used. And structured loss idea is very simple. If you think about triplet loss, what it does is it does sample by sample. So you take 3 samples and you create this loss function. Now, what structured loss helps in doing is, it, because we sample these batches in most of our training, what it does is, from a batch, it will create many such triplets basically. So from a batch, you can create all sort of permutation of positive and negative samples, and that's what really structured loss was about. It was just about computational efficiency of creating these triplets from a single batch, mini batch of data. Instead of doing it sample by sample. So it made it more computationally faster.
So I didn't understand how the margin helps with not collapsing. So in your digit example, if the network collapsed everything to a single point, like all the 3's 1 point, all the 4's 1 point, they will still have a margin between them, because the margin is about other classes, right? I mean, how does it help the margin? How does margin help against collapsing? Or does collapsing mean something else?
In my understanding, collapsing just means that, just collapsing them into a single point in this latent space.
What is that?
Sorry.
All images into one?
Right.
Can you go to the next slide, please?
Next
I think the loss function would be.
So if you collapse everything into one, then everything will be similar. You wouldn't be solving the first problem either, right? I thought the problem was collapsing each class into single point, meaning you lost all the variabilities, etc. So if you collapse all of them into 1 point, then nothing will be dissimilar. So that loss will be huge, right? The dissimilarity loss will be huge. So I feel like there is more to the story, in the sense that even for the triplet loss, you are taking a. So does the triplet loss uses mini batches as well, or is it that
triplet loss originally was, originally triplet was not mini batch based. It was just 3 samples, and that's why it was like super slow. But the structured loss is basically a mini batch version of triplet loss.
And where is that here?
I haven't.
I see 2 lines.
Yes, I did not write. I did not write that. I just wanted to. I did not write that. It is not here in the present.
Okay, what's the second line here then?
So the first line is the contrastive loss, this A1, which is just doing it. These 2 equations are the A and B of this figure.
So even the first line has an alpha then?
Correct. Yes. There. Yeah. Yes.
And in what way is the second line better than the first line?
I think in terms of just, just looking at it, it's the same, but the empirical results were better with triplet loss. And there might be some proposal of why, some conjecture. So my hypothesis of why it was better, but empirical results were better using the second formulation.
They are not identical. One has only essentially one max, the other one is first adds it. And
yeah, Professor, just to answer one of the questions that I realized. So you said that, I think the reason is this alpha needs to be included is because of this max. So it chooses max of 0. So this can never be negative, this value. So it might collapse it into 0 because of this, the way the loss was proposed. So if you think about it, this would be positive, right? So if alpha is not there, this value would come out to 0.
Yeah, but I mean, obviously you could have just minus of the second red term and it will work. But the way they formulate it, right, there is no additional benefit if you open the distance between them more than alpha. That's not giving you additional value, because when this red term becomes larger than alpha, meaning you open up them too much, right? Then that score still evaluates to 0.
Correct. So that's all we wanted. We just wanted to push it till alpha. Beyond that, we don't care.
Yeah. So maybe
because this latent space is limited, right? So, and you're trying to put all these high dimensional vectors fit into it. So it's not like you can like push it super far or insanely far, because that doesn't really help us. It's really about using this latent space well as well. So all we care about is pushing it some alpha apart, which is what we control.
Yeah, I agree. I mean, at the end, this is almost like the inverse problem of not collapsing. You could just spread things infinitely.
Correct.
Makes it the easier thing, but this is trying to keep everything still within somewhat alpha of each other.
Right. Yeah. Yes.
But even the first line is doing that. So there has to be more to the third line somehow.
I see.
Maybe.
So, but the alpha question got answered, right? But now you're talking about this one and the what is the difference?
Yeah.
Yeah.
Okay. So the alpha question is really trying to keep things not too far apart,
right?
So that you don't cheat by just spreading things.
I think it may be just related to triangle inequalities. I'm trying to like something. The latent space, maybe they are. Since you are just
there will be a reason why. Yeah, so I think I'll need to look at motivation of triplet loss. Let me make a quick note and I'll come back to this.
Okay. All right.
This is not allowing me. No. Okay. Moving on. So now the next one is actually I'm not listing all of them. I'm just trying to list. I'm not listing all the chronology of it, but just the important landmarks, which I think are important for the understanding the continuity of development till the final loss that we go to. So I think n-pair loss was one of the it doesn't look like that big a change, but it turned out to be surprisingly useful later. And what n-pair loss does is basically these two things. It uses soft plus instead of this hard max operator, which was max 0, x, which we were using in the previous slide. Instead of that, it uses a soft version of that, which is log 1 plus ex. So that's how this loss is formulated. It helped get rid of margin, and I don't have an answer to that question, that why alpha was no longer needed. but I think it has to, I mean, my knowledge is a little limited on this topic, that, you know, why this loss really got rid of alpha. And I bet it has to do with the shape of this soft plus versus this soft max versus hard max. So that question aside, basically they replace that max 0 comma, you know, x operator with this, and this is basically the triplet loss written, and then they also batched it. So this is written in form of a, you know, all the pairs in a batch. So given this batch, you create these so given this batch, you create these you know, just the positive pair and all n-1 negative pairs, and then you create this loss function with, you know, positive being, you know, minimized and negative being maximized, and that's why this is called n pair loss. So it's a loss between n pairs. That's what this figure is trying to say. But if you know, just do a little bit simple mathematical manipulation, this loss can be written as, you know, this, and this starts to look a lot like multi-class logistic regression, and that's where it really you know, got into probabilistic perspective now. So from next slide, basically the next slide would be about you know, thinking about it in a more probabilistic sense. Again, I'm skipping a lot of details because my motivation in this session was to give a brief survey. I have given all the references for you to check out, and we can cover in more detail of whichever topic people would like in the next session. But if you...
So, one question, so just general, you know, why do, you know, like you create one positive example, but many negative examples?
So I think there is a probabilistic interpretation to it. I'm thinking of a normal, because we haven't talked. So probabilistic interpretation is kind of this term, this negative sample term, is trying to approximate the partition function. So the more you have, the better the approximation. And there is a information theoretic perspective to it as well, which I was going to show next. But I'm thinking of why I think what people noticed in when they were using triplet loss, I have read it somewhere. I'm just trying to recall it. So when they were doing triplet loss, training using triplet loss, it was just pushing two positive samples together and one negative, you know, just two negative samples, sorry, apart. But it was not very, you know, efficient way of training, because for every anchor point, there are a lot of negative samples, and you want all of them to be pushed apart. If you just do it for every epoch, if you imagine doing it only one, because these positive negative pairs are formed randomly, just because there are a lot more negative pairs than they are positive, you would need to do a lot more negative updates. I don't know if that makes sense.
From, you know, availability of data.
Yes, so
it does make sense. So basically, mini batch is, say I have 10 of each digits, right?
Yes.
So trained one as the anchor, I have only 9 other ones, but I have 90 negative ones.
Right.
At that. So there is, you know, just, you know, arithmetically, it does make sense somehow. But yeah, I mean, of course, you know, since you are deciding what to call positive, negative samples, you could rerun the positive samples if some balancing was needed. So anyway, so it looks like it's more, you know, trying to do the negatives more than positives together.
But if
So
you see,
I'm wondering, you know, what's why exactly 1 to the n-1 ratio? But okay,
yes, it's actually not a ratio, Professor. If you see, the weight of the positives is higher. So if you see, for every negative, the positive is subtracted, right? So so basically, for every negative contributes 1 by nth of a positive, right, overall. So the same positive is subtracted for every negative, right? So so the weighting is same, so that you bring the same 2 positive samples, say 10 times closer, and you push 10 negative samples 1 apart. Just, you know, just making up numbers.
Okay, I see it.
Yeah, okay. All right, so the infoNCE NCE loss, as it's called, it was proposed in the, you know, contrastive predictive coding paper. And what they motivated in a different fashion in the paper, and you can read it, but I prefer the motivation that I'm going to present. So what I think the notice was these terms that are written can be written more generally. So you can think this is basically, you know, just a similarity between the embedding of, or, you know, the transformed version of X and transformed version, excuse me, of Y plus. And you can have other forms of similarity metrics. So they basically said, you know, we're just going to replace it with a general function of f of y plus x, and all it, you know, all it's really about is, you know, how similar they are. And they showed, and you can see the Oord reference paper, that in the optimal case, if the optimality is reached, this function f y x really approximates a density ratio. And what this density ratio is saying, just intuitively, is, hey, given x, whether this y came from the joint distribution pxy versus whether this y just came from the marginal. If yes, this density ratio would be high, and if no, this would be close to 0, because that y did not come, the negative sample did not came from corresponding x. So that they show that this really holds, that the optimal f value is really proportional to this density ratio estimate. And further, they also show that the optimal ince loss really gives this lower bound on the mutual information between the positive y and x. And this is the exact bound. How they do it is given in the paper's appendix. It's actually a very simple proof. Maybe I'll cover it in the next session if there will be interest and time. But if you see, the question that you asked, there is a mutual information based perspective to it, that as n increases, so they want to increase n, they want to have more negative samples. So this really becomes, because we want to maximize left hand side of this inequality, because this becomes larger. So it gives better bound on it. So
yeah, so sorry, just in terms of our previous structure, what is fyx? I mean, it's y and x pushed through a identical network, and then some metric on it. What's the formal way of fyx?
Okay. Yes, let me just finally use.
And if you go one slide before, was it also fyx there, or what was it?
Yes, so let me just show you the previous slide. So there we have
just f. Yeah, this was still following.
Yes,
you did a quick hand waving, and now we have fyx. Yeah.
Yes, so I'll explain you. That's a, yeah, you know, I missed out that detail to explain, but I'll explain what the exact question. So basically, as I said, that because the loss function started to look a lot like multi-class logistic regression, they really build upon that. So what this fyx really says is, given x, I basically so given this set that we created in the x, y plus and n-1 y minuses, we create a new set where we assign label 1 to y, and all the y negatives are assigned a label 0. So basically we create an alternative multi-class classification problem, because we know corresponding to x, this y is the positive sample and this is negative. And once you have this, what you do is multi-class logistic regression. So to answer your question, fyx is basically the output of a softmax, which n-way softmax. And we were just trying to classify the positive sample correctly. So say this unit, and what this so the way it's obtained is, you know, just passing the y plus through a network y plus, and saying, hey, this should be 1, and passing any y minus through the network and saying this should be 0.
How do I input x?
You don't. You use the x to transform this problem into multi. This actually, this binary classification. I think I made it confused, but yeah. So basically, you use x to form this problem, transform this problem into something else. So your f is just taking y as the input.
Okay, but then when it comes to calculate f star of y comma x or anything, I need to plug in x, right? I mean, how am I getting out of?
Okay, yes.
Not.
Yes, you are correct. So I think to just trying to be concise, I missed some important information. So there is a symmetric term used in all the NCE losses. So you are correct. So typically, so the way it works is, final NCE is, you can think of it as NCE with respect to x plus LNCE with respect to y. And I showed you the one with respect to x here, and there you can form a similar formulation based on y. So you will have a y plus let me write this way. Oh, my bad. Sorry, just a second. Let me just, so you will have a y and corresponding x plus and x minuses, and you will calculate in the same fashion the second function. It could be the same f, it could be a different f. People have there is a slightly different proof of if you use a different f for x and y, and but this proof is if you are using the same f, so you can use this exact same f to, if the modalities are same, basically you can use the exact same f and calculate the corresponding to x as well, corresponding to y as well. So y being the anchor.
So, okay, but again, L, as I understand, is a loss function.
Correct.
For me to train F.
Correct. Yes.
So at the end, I have an F, according to you, that only takes one
right
of vectors. So again, how do I calculate f star y comma x? At some point I have to use it, and supposedly it's a density ratio.
So
it requires two things. Even a density ratio requires two instances of vector y and x. So I need the operational definition of calculating to f y comma x.
So f y comma x would be in a perfectly trained network. If you have f star, if you have obtained f star, if you give x to it, and so you say you have a pair x comma y that correspond to each other. If you give x to it, it will give you some value, some scalar value. If you give the corresponding y to it, it should give you sorry, wait a second. So this density ratio is actually ordered, right? So it does not necessarily need to give you the exact same value. So so if you want, say, the way you decide the order, it will depend on that. So if you want f star y comma x, you will put in y. If you want f star x comma y, which would be Ex given y upon Px, you will put in x. Did I make sense?
I don't think so. I mean, because then you are saying there is a f trained for each instance of y, and f trained for each instance of x that's ready to plug in the other variable. That doesn't make sense. I mean, I felt like there was only one f we were training, and it has to, universally be able to compute this y comma x. I think something is
yeah, you are correct, because once you made that comment, I realized that the way they presented the proof, they had an individual f. So I think maybe I'm missing something here. I'm definitely missing something here. So let me come back to this hopefully next session.
All right. Okay.
All right. So sorry, the time's up. So I just saw the clock. It's 5:13 already. So I would just stop here for now. And just let me know the questions even after the presentation, and I will try to touch upon all these topics that we discussed that remain unanswered today, and finish the presentation in the next session. I think that will consume all the second session time as well. So we won't get to any tools and stuff, so which I can do later if time permits. So
So actually, maybe we go to the slide where we talk about different loss functions.
Different loss functions. Okay. Different loss functions. Was this maybe this one?
Oh yeah. So can I use like similar loss function, let's say for transfer learning or like domain adaptation?
So I mean, this is, first of all, this is essentially doing transfer learning. If you think about it, I mean, this figure itself tells you that this encoder is trained for transferring knowledge. Right? So just fundamentally, self-supervised learning is doing transfer learning inherently, right? So you train on this pretext task and you transfer that knowledge to the downstream task, right? So all of them are doing that, short answer. So yes. The other part you said was transfer learning, and you said something else, domain adaptation.
Yeah.
So domain adaptation can also be done, I feel. It can be done, but it will depend on how you formulate the problem. I'm just thinking. So there is a paper, I think it's called Coral. And there are other works as well, of course, but this is just this is something that I remember, and it's very highly cited. It's called correlation alignment, and what they do is basically calculate this some feature. So you takes one of these Z's and calculate a statistic based on them, which they call correlation, and they align them. Aligning is literally doing this, pushing them closer to what they were earlier. So yes, it has been used for domain adaptation, but they don't call it, or they don't see it in this perspective, but that's basically what they are doing.
Okay, I see.
Yes.
So I was talking about, can you send like maybe the name of the paper you were talking about to chat?
I just search for correlation alignment paper or Coral. Correlation alignment for unsupervised domain adaptation.
Okay.
Yeah, that should be the one, I think. I think it's Sun, Feng, and Sainko.
Okay. Oh yeah, I found that.
Okay, great.
Okay, yeah, awesome. I will take a look.
Yeah, go ahead.
Okay, thank you.
Yeah, no problem. Have a good one.
Bye.
Nitin, you had a question?
So how does the pretext tasks seem to be pretty important, right, in terms of understanding the whatever problem space, I guess. So like, how will you, if signals are kind of weird, then how will you come up with a predefined task? Like for image or time signals, it's kind of like this. But if there is something, say graph-based signals or some social network kind of signals,
yes,
or some other weird signal that you come up with, like, is there a general recipe for finding the predefined pretext tasks, or?
Right. So maybe
Yeah.
I hope to cover some of it in the, so that's like kind of where we were getting at. So really, think about what you want in the features. So that's how you will define your pretext task. So just looking at this slide, this is where we stopped today. But say so this is a predictive pretest task, which is like self prediction one. So right, so you predict something using something. So say you predict V2 using V1. So what will Z have, or try to have? Everything that is common between V1 and V2, it will try to have that at least. Right.
Mm-hmm.
So this was really the slide about how predictive learning tries to, so
Okay.
Z tries to really have this part in case of it wants to keep this to be able to do prediction.
So even in pretext class, like even you define like a sub categories of pretext classes, right? Like a bunch of in the beginning of the slide, you said like it could be like either puzzle kind of thing.
So, so let me finish my answer. I understand. So let me finish my answer.
So which one is like, is there like you have to use all of them to solve a particular classification problem, or like is one better than the other?
Right. So it will really, again, so as you said, it will depend on your downstream task or set of downstream tasks. So the pretext task would be designed. So the general self-supervised learning, originally they proposed, and I don't think that's appropriate, but they propose that we want to learn some general features. I'm assuming the idea of general features is keep all the information in X in a smaller dimension. That's the only way to keep absolutely general Z, right? It has basically X and Z have all the, Z has all the information of X. That's the only way to create. But I don't think that really ever happens. So Z, to create Z, you throw out something from X, you keep something from X. And whatever you keep, you want to make sure that your downstream task is a subset of it.
Okay.
Right. So that's the just the high level idea. So you will need to think about what downstream tasks you want to do. Although originally people said that we just want generic features, I don't think that will go very far. It doesn't even make sense. How can you keep absolutely general features unless you have all the information in X of X and Z. So the question you are, I don't know if I answered.
Yeah, okay. Yeah, that's because like everything is based on all of whatever feature you learn is kind of dictated by the pretext task, and then you. But is there like further refinement? Like, do you retrain your networks after?
Yes. Absolutely, yes. People do that. Yes. More often, mostly they do that. Yes, most of the time.
So you get the feature. You have the neural network that gets the features from pretext task, and you use that as initial point for
correct
the downstream task.
Yes, absolutely. And I mean, that officially referred to as semi-supervised learning, and that's what most of the time people are doing, because for the downstream task you need labels, but the advantage is that you get away with fewer supervised data.
Okay.
Because you initialize in this good point.
Okay.